Okay, another pathways problem, 1.44. This one deals with the concept of density and making measurements as it relates to significant figures. I think this problem is kind of cool. It's a little bit fun because it's a little bit more hands-on and practical, and that makes it a little bit more fun than just working problems out of the textbook. So the question outlines an experiment in which you're trying to figure out which metal do you place into a graduated cylinder. We're going to do this through the measurement of density. The problem starts by stating that you fill up a graduated cylinder with a column of water that's 25.0 milliliters. So this is kind of the before case, or the initial case. You have just 25.0 milliliters of water in your cylinder. And then you're going to drop in a chunk of an unknown metal. Now that metal is either going to be zinc, iron, or perhaps it's nickel. Each of these metals have their own corresponding densities in grams per milliliter. Of course, these are physical properties of these different metals. So the hope is that we can measure the density in the experiment, figure out which metal it is, even if we don't know. So the initial volume is 25. We drop the chunk of metal in, and the volume increases. And this is because, of course, the metal takes up some volume. Now our hope to figure out what the density is, and just to remember, the formula for density is equal to the mass of an object divided by the volume of the object that's under study. Now here, we're going to use the usual units of grams per milliliter. Okay. Now we're told in the problem that the metal chunk is exactly 25 grams. Okay, so we know the mass is 25.0 grams. The trick, of course, is figuring out what the volume of that object is. And we're going to measure that here by the water displacement. So the metal takes up some space or some volume. We drop it into the column. Of course, it'll sink because it's more dense than the liquid water, and the volume increases. Now that difference in volume then tells us what the volume of the metal is. It's just measuring the volume of an object by water displacements. Centuries-old technique. So the trick is to figure out what that final volume is. Now they give you pictures in your textbook in this problem 144, and you have to basically make the reading yourself. And that's another thing to kind of learn. But I tried to draw this as good as possible to reproduce what your textbook is showing. But obviously the picture is a little bit different, okay? But the key idea is that there's these graduations. There's one at 25, there's another major tick mark here at 30, and then we've got one at 26, 27, 28, 29, and they even give you 0.5 tick marks. Okay, I've dotted these here to kind of highlight them. Now what we see is if we look at the column of water in that picture, there's a meniscus at the bottom. That meniscus is usually a curved surface, and usually in lab we make measurements at the bottom of that meniscus. Right here, the bottom of that curved surface, okay? Now, when I read this graduated cylinder, I can clearly see that the bottom of that meniscus is somewhere between 28 and 29 milliliters, okay? Clearly, this is 28 and that's 29. It's somewhere in between, okay? But what should I report that final volume as? Now, an important rule to learn about for laboratory work is when you are making a measurement in lab, you are always allowed to use your best judgment to estimate one digit of precision. You can estimate only one digit using your best judgment. Now, what do I mean by that? Or how exactly might that work? Okay. Well, I know that my volume reading is more than 28. It's more than 28. So it's going to be 28 point something. Because it's not quite 29. If it's 29, it'd be way up here, but it's certainly more than 28. Now that one digit of precision, I can't read. I don't know exactly what that digit should be, but I can make an estimate. For instance, this is 28.5 right here. It's below that, clearly, and it looks to be even a little bit below halfway between the 0.5 and the 0 mark, okay? So if I'm looking at this, I might read 28.2 milliliters as my final volume, 28.2. I estimated that 0.2. I took a best guess. Now, would I estimate more digits? No, because my eyes aren't that good. I can't look at this picture and get a second and third and fourth digit of estimation. But I can estimate 1 just by convention, and my final volume then can be said to be 28.2 milliliters. That's my final measurement. Now if I want to figure out the volume of this metal that I dropped in there, I simply compute my change in volume that occurred. Now my final volume, of course, was 28.2 milliliters. That's after I dropped the chunk of metal in. And my initial volume was 25 milliliters. So to compute the delta volume, or triangle volume, we call that delta in chemistry. It denotes change. Whenever you see the triangle, we talk about change. So to compute the change in volume, I have to do a subtraction exercise. I have to take 28.2 minus 25. Now, of course, the answer there is pretty clearly 3.2 milliliters, right? We can do that in our head. But what I want to remind you about right now is the rules for significant figures again, because this is a prime example of where this would come into play. These volumes were measured, so we don't want to over-report precision, digits of precision in our answer. Now, what's the rule for addition and subtraction? Well, remember that we look for addition and subtraction, you've got to look at the number of decimal digits. Here, we've got 1 decimal digit, so our answer should also have 1 decimal digit. And sure enough, that's what I've reported already as my volume. Okay, so I kind of got lucky in this case that I honored the sig fig rules. But you need to remember consciously to think about that at this point, because you've done a mathematical operation, and you need to make sure that those rules are honored. But nonetheless, I'm good to go. I can put that 3.2 milliliters down here for my volume, and then I simply do my division. If I work that out just on my calculator, okay, at first, it looks like I get 7.8125 grams per milliliter. Now again, I've done a calculation based upon measurements that have their indicated digits of precision, or indicated sig figs that are associated with it. I need to think about my sig fig rules in terms of how I'm going to report my answer. Okay, my final answer. This is just what my calculator gives me. I haven't thought about sig figs yet. So thinking about sig figs would yield what? Well, it looks like to do my density calculation, I do grams per milliliter, I do division. And the rules for multiplication and division is that your answer can have no more significant figures than the least precisely known variable. Here, that's my 3.2 in my denominator, because there's only 2 sig figs here, okay? So my answer must also have 2. And it looks like what I should do to achieve that is simply round to 7.8 grams per milliliter. And that should be my final answer for my density. Now back to the original question. Can I tell which metal I've got just based on my computation here and my change in volume, my measurement of density? It looks to me like that metal was most likely iron. Iron had an accepted density or stated density of 7.87 grams per milliliter, and that's by far the closest to what we've got over here when we actually computed 7.8. And in fact, we could, based on our measurements, if there's no systematic error or no inaccuracy, things that went wrong, like our graduated cylinder was calibrated wrong or our balance gave us the wrong mass, in the absence of that, we could be very confident in excluding zinc and nickel from being a possibility here, okay? So this is a nice example problem that not only shows density. You'll want to know that for the exam in grams per milliliter. It's pretty simple and straightforward. We'll want to use that as a conversion factor going to grams or volumes, what the idea is in terms of its being a physical property, so we'll want to understand that. But another nice thing about this problem is it shows not only measurements, the estimation of a digit, but also the importance of your significant figures for chemistry as a measurement science, okay? So it's kind of a cool little problem, pretty straightforward and fun.